Hello again, everybody. This video is building off of the ideas of impulse from the last video. Remember, it's this equation that's relating force, time, and what we learned was this thing known as momentum. Now, impulse has two important applications that you need to know. All right, the first is us looking at a graph of impulse or of force and time, and one of my favorite topics actually is safety. What is the physics of safety and how does this relate to impulse and momentum? That's what we're getting into for kind of part two. Okay, so starting off, we learned about this impulse equation, and again, I mean, technically there's that letter J you could use if you watched the earlier video, but most of the time it's written like this. No one really asks you to calculate the impulse of, say, a collision or something. All right, but this equation allows us to relate forces and times and masses and velocities. So one thing you could do with this equation is use it to analyze a new type of graph, a graph that we haven't seen before. This is a graph representing the force of an object, and this should be net force, just so we're clear. Okay, this should be the net force acting on an object over some amount of time. That's what I have down here on the x-axis. Okay, well, if I was looking for that area under the curve, just maybe for fun, maybe right here, I was looking at this area under the curve. I have an area. Now, that's just a square, what I made there, so the area is going to be equal to the base times the height. The base is equal to 3 seconds. The height is equal to 2 newtons. Oh, okay, so I have force and I have time being multiplied, right? I could just rearrange this real quick. I have the 2 newtons there and the 3 seconds right here. So I have a force being multiplied by a time. Well, wait a minute. From this equation, what is the force multiplied by a time? It's the change in an object's momentum. Oh my gosh, we have another important graph, a force versus time graph, the area under the curve. It gives you the object's change in momentum. Area gives you the object's change in momentum. That's huge, and that's pretty similar with a key difference to another graph we saw. It gives you the object's change in momentum, mv minus mv naught. So maybe if you knew the mass of the object and maybe you were told it started at rest, you could actually figure out the velocity pretty easily from this graph. This is another one of those examples where you knowing this kind of quick tidbit, this quick fact, force versus time graphs, the area gives you a change in momentum. That gives you a powerful tool at your disposal. And for the AP Physics 1 exam, they love this type of graph because it's not obvious. Okay, if you don't really know a good deal of physics, you overlook this implication that the area gives you additional info about an object, namely its change in momentum. Now, if you remember from our last sequence of videos, we saw that force versus x, that area under the curve, that gave you the work on the object. Or, if it was the net force, it gave you the change in kinetic energy. Oh, so we have two graphs. I know they're pretty similar. There's forces on both sides. Both of them gives you a quantity that is changing, either the change in kinetic energy or the change in momentum. But the key difference, this one here is versus time. This one is versus displacement. College Board loves these two graphs. I have seen a question, usually actually a couple of questions for each of these. Maybe not for both, but at least maybe 3 questions, 2 for one, 1 for the other. But I always see questions on the AP Physics 1 exam that has these two graphs on them. And you gotta know, or at least be smart enough to quickly derive it or see it on the AP equation sheet. Force versus time, well, that gives you the object's change in momentum. Force versus displacement, that gives you the object's work or the change in kinetic energy. So very important things to recognize. Two very valuable graphs and graphs that College Board loves. And therefore, if you're taking an AP Physics 1 class, like if you're in my own class, these graphs are very important. So force versus time graph, the area under the curve gives you the object's change in momentum. Okay? That's the first part. Second part, we're kind of switching gears, okay? Let's think about safety. While we've learned about forces in our sequence of videos, we haven't really talked about what it means for something to be safe versus unsafe. And, you're certainly on the right track if you could imagine, well, probably more force on an object means it's less likely to be safe. If you want to be nice and secure, if you want to be surrounded by niceness and not be in danger, you're probably trying to avoid forces. But how do we avoid forces? How do we ensure that the forces that are acting on objects in maybe some kind of collision, some kind of impact, how do we help try and keep those forces low? Well, let's think about things that kind of are typically thought of as safe, where there isn't a lot of force, like airbags or boxing gloves, right? You wear boxing gloves because you're trying to keep your opponent, maybe your sparring partner, safe. When you're landing on a trampoline, that's normally safer, so to speak, than landing on some hard concrete. Especially when you think of their alternatives, right? Imagine a collision where you're hitting an airbag in a car versus like the steering wheel or the dashboard. Okay? Boxing gloves versus being hit by a solid fist, or maybe like a wall, maybe like a baseball bat. Oh my gosh, not to get morbid, but those things that are much harsher, much harder objects. Or landing on a trampoline or one of those kind of gymnastic floors that have give versus landing on maybe hard concrete. Why are these objects considered more safe? And what a lot of people might say is, well, they're softer. And that's not bad, and that's certainly related, but there's no physics of soft. Soft isn't a quantity we put into equations. So what is the physics that's going on that relates the material, maybe the softness, to decreasing force? It's actually all about the impulse equation. The impulse equation is exactly why this diagram, this photo here, where you see this car, man, look at this. This car is destroyed. This is entirely on purpose. And that's actually surprising to a lot of people. This design here, where this front of the car, right, there was a good maybe 3 feet or so more of this car that existed before this impact. Well, this is totally by design to keep you safe. Why? What's going on? To understand this, I'm going to set up an example. Imagine I have 2 eggs. I go to Safeway, I go to the store, and I buy a couple of eggs. They're identical, they have the same mass, and I bring them to my room, and I set up a nice soft pillow, and also just a hard, basic red cement brick. Okay? I'm going to drop both of these eggs. One of them is going to land on the soft pillow. One of them is going to land on the much harder brick. But I'm going to release them from the same height. So both are going to fall the same vertical distance. Now, of course, after I drop them, what do you probably notice if we did this in real life? The egg that falls on the pillow, well, there's a good chance it's nice and safe, right? It's probably not destroyed. But oh my gosh, the egg that hits the brick, oh, it's probably obliterated. It's cracked, it's smashed, the yolk is all running out. What is going on if I have the same eggs, okay, they have the same mass, I'm releasing them from the same velocity? What exactly is happening? Let's figure it out. If I am dropping these 2 eggs from the same location, an important thing to recognize is this right here. Both of these eggs, right before impact, the nanosecond, the millimeter before they hit the same level, right here, they're going to have the same velocity. I'm not going to prove it in this video. You could either do that for yourself using maybe a conservation of energy setup or maybe a free fall setup. But if I have 2 objects that start at rest and they fall the same distance, they're going to have the same velocity at some later similar height. So both these objects have the same final velocity. And that means if they had the same initial velocity and the same final velocity, both eggs have the same change in velocity. Does that make sense to you? They both started at rest. They both have the same velocity right before impact, so they have the same change in velocity. Well, that actually means something very important. That means that both eggs must have the same change in momentum. How am I getting to that? How am I concluding that? Well, P equals mv. So the change in an object's momentum, the mass can't change. It must be the change in the object's velocity. So if the 2 eggs have the same change in velocity, they must have the same change in momentum. With me so far? Okay, well, let's now remember the impulse equation. Force multiplied by time is the change in momentum. Both objects have the same change in momentum. So what does that mean? If one scenario takes a larger amount of time, it must also be applying a smaller amount of total force. Something just popped up on the screen. Because they have the same change in momentum, making this side t large If I have to get to the same value, it must mean the force is small. Oh my gosh, you just saw things change on the screen. My slide actually crashed on me. I had to reset it. My apologies, but I have all the same information there, and I did add something here. So if you need another example of why this is true, again, I have the same change in momentum going on. Let's say what I have right here is kind of a sample math problem. Some people like to think about this more mathematically. So I'm going to have 100 for both of these eggs. That's what I have right here, kind of the two different examples. Okay, they both have that same change in momentum. Well, from a math perspective, if the time of impact, let's say, was 1 second, whatever it was, maybe it's for the brick. Let's say it took 1 second. Well, what must the net force acting on the egg be to make this equation true? What does it have to be? This is easy. It has to be 100 newtons, right? Because 100 times 1 is 100. But notice, by doubling this number here, by doubling the time, now what would the net force be? Oh, it would be 50 newtons. By doubling time, by increasing the time, I made the force smaller. That's the idea. Now, you can't compare apples to oranges. I can't compare dropping an egg on a brick versus, say, taking an egg, climbing up to the top of the Empire State Building and throwing it off, because those would have very different changes in momentum. But if you have, say, the same objects and they have the same change in velocity, well, if your only difference is that one impact takes more time than the other, well, the impact that extends the time decreases the force. That's the idea behind all these safety things. This person who is falling, whatever their mass is, whatever their change in velocity is, well, them landing on a trampoline and the time it takes that trampoline to bend and stretch, that increases time, so it decreases the force, say, compared to landing on hard concrete. Same person, same change in momentum, but landing on concrete, that takes a very short amount of time, so a much larger force. Similarly, if you compare your own head going 60 miles an hour when you're driving your car, hitting a steering wheel, that's a very short time of impact, so a very big force, versus an airbag, which is designed to deflate really as you hit it and compress and smush that airbag. More time, less force. Okay, you being hit by a boxing glove versus a bare fist, say the same pushing motion, well, more time in that impact, less force. Modern cars are designed to get wrecked in a collision. Okay, I kind of like this visual right here. If you have a really small time, you must have a giant force. If you have the same change in momentum, I try to make that the same size, and you have a much bigger time, the force is tiny. Modern cars are meant to be obliterated like this because all this crumpling and bending and warping of the front end of the car, all of that takes time. My brother's very first car was an old 80s Lincoln Continental. Old cars were built like tanks, solid steel, all of that. And when they got into collisions, man, it was like they were barely damaged. But that was actually terrible for you, the passenger. Because if that car just came to a stop instantly without any bending or warping, that means there was a much larger force applied. Just to take this one step further, this is a reason why electric cars, for many reasons, are far safer, because there's no engine up here. So this entire front section of an electric car can much more easily bend and warp without big, heavy things like engines getting in the way. So impact, safety. How do you keep someone safe? How do you decrease the force acting on them? You do it by increasing the time of a collision. Because if two scenarios have the same change in momentum, more time of impact means less force. That's the physics of safety. Okay, that's it. We looked at a graph of the impulse equation and how the impulse equation is really the basis of all things safe in our society. That's all. Thanks a lot for watching.